There is a version of the ocean you have never seen. It does not glitter. It does not shimmer with schools of silver fish threading the light. It does not hum with the low songs of whales. It is still, not the stillness of rest, but the stillness of absence, the stillness of a room where something important used to be. Beneath the surface of thousands of places on this planet, coastal shelves, river mouths, open seas, even freshwater lakes, there are zones where the oxygen has run out, where the water has become, in a very real and scientific sense, breathless. Scientists call them hypoxic zones. We call them dead zones. And yet, this word, dead, is not quite right, because even in these dark and oxygen-starved waters, life finds ways to persist. Strange life. Slow life. Life that has learned to wait. Tonight, we are going to travel through these zones together. We are going to visit every major dead zone on Earth, from the Gulf of Mexico to the Baltic Sea, from the Black Sea to the coasts of West Africa, from the Pacific shelves to the rivers of China. We are going to understand how they form, why they persist, what they mean for the ocean, and what they reveal about us. This is not a story of doom. It is a story of understanding, of learning to see a world that breathes, and to recognize where the breathing has become labored. So let your body settle now. Let your breath slow. The water is dark, and the current is gentle, and we are going to descend slowly into a world that most eyes never see. Before we travel, we must understand. And to understand dead zones, we must first understand oxygen, not as something we take for granted, but as something the ocean has to work very hard to maintain. Water, unlike air, does not naturally hold much oxygen. The ocean absorbs it from the atmosphere at its surface, and it is produced in shallow, sunlit waters by phytoplankton, the microscopic plants that drift in their billions near the sea's upper skin. This oxygen is then carried downward by currents, by the slow turning of deep water, by the physical mixing of waves and tides. In a healthy ocean, this system works. Oxygen reaches most depths. Animals breathe. Bacteria decompose. The great cycle turns. But when this system is disrupted, when too many nutrients pour into the water, when stratification prevents oxygen from descending, when decomposition accelerates faster than replenishment, something happens. The oxygen disappears. Hypoxia is a scientific term. It means low oxygen, specifically waters where dissolved oxygen falls below 2 milligrams per liter. Below that threshold, most fish cannot survive. Shrimp and crabs begin to flee. Slower creatures, mussels, worms, some starfish, are left behind to face the crisis alone. Below 1 milligram per liter, we reach anoxia. No oxygen at all. In these waters, the only survivors are certain specialized bacteria, and they do not need oxygen to breathe. They breathe sulfate instead, and as they do, they exhale hydrogen sulfide, a colorless toxic gas that smells of rotten eggs, and that is lethal to almost every complex creature on Earth. This is the anatomy of a dead zone. Now let us ask how they form. The story almost always begins on land. Rain falls on a field. That field has been fertilized. Nitrogen, phosphorus, the chemical wealth that makes crops grow tall and fast and plentiful. But the soil cannot hold all of it. Some of it runs off, carried by rainwater into streams and then into rivers. The rivers carry it to the coast. The coast receives it like a gift it cannot refuse. These nutrients, nitrogen and phosphorus, are in the ocean what they are on land, growth fuel. They trigger explosions of phytoplankton, blooms so dense the water turns green, then brown, then rust-colored. From the air, these blooms can look almost like oil slicks, vast and spreading, and then the bloom dies. Billions of tiny organisms sink to the sea floor. Bacteria feast on the dying mass, consuming oxygen as they decompose it. If the water column is stratified, if warm, lighter surface water sits on top of cooler, denser, deep water, and the two cannot mix, the oxygen consumed by decomposition is not replaced. The deep water runs out. This process is called eutrophication. It is one of the most well-documented environmental changes on Earth, and it has been accelerating since the mid-20th century. Since the invention of synthetic fertilizers, since the industrialization of agriculture, since the world began to grow more food for more people than had ever existed before. The zones were always there in small ways in natural places, but in the last 70 years they have grown, they have multiplied, they have deepened. There are now more than 400 confirmed dead zones on Earth covering more than 245,000 square kilometers of ocean, an area roughly the size of New Zealand. Let us visit them. We begin in the Americas, in warm water. Every spring as snow melts across the great interior of North America, the Mississippi River swells. It is one of the longest rivers on Earth, draining water from 31 states, from Montana to Pennsylvania, from Minnesota to Louisiana, and carrying everything those states have shed into its current: topsoil, sediment, and fertilizer. Enormous, relentless quantities of nitrogen and phosphorus from the cornfields and soybean fields and hog farms of the American heartland. All of it flows south. All of it pours into the Gulf of Mexico. And what happens next is almost clockwork. By late spring and early summer, the nutrients trigger blooms. The blooms die. The decomposition begins. And in the deep water of the Louisiana shelf, in a zone that shifts and pulses like something alive, the oxygen disappears. The Gulf of Mexico. Dead zone is the second largest in the world. In some years, it has expanded to cover more than 22,000 square kilometers, an area larger than the state of New Jersey. It drifts westward through summer, pushed by currents, occasionally breaking apart, occasionally consolidating into a single, vast, breathless mass. Shrimp, the Gulf's most economically valuable catch, are perhaps the most visible victims. When the dead zone expands, shrimp flee to shallower, oxygenated water. They crowd together. They become easier to catch briefly, but the fishery is smaller, compressed, stressed. Shrimpers who have worked these waters for generations speak of changes in their catch, of the zones they now avoid, of the slow erosion of something they cannot quite name. On the sea floor within the dead zone, the community of bottom-dwelling creatures collapses. Polycate worms, hardy, primitive, ancient, persist longer than most. But even they reach a limit. Below a certain threshold, the bottom becomes a gray and empty plain. There's a moment, scientists call it a turn event, when late summer storms stir the Gulf, mixing the stratified layers, pumping oxygen back into the deep. The dead zone fractures and retreats. Fish and shrimp return. Seafloor begins slowly to recover, and then the following spring, the river rises again. This is the rhythm of the Gulf. Annual, reliable, deeply tied to the agricultural decisions made hundreds of miles away, in states that have never seen the ocean. Cross the Atlantic now. Travel east, into a different kind of water. The Baltic Sea is an enclosed world. Surrounded by 9 countries, Sweden, Finland, Russia, Estonia, Latvia, Lithuania, Poland, Germany, Denmark, it is fed by rivers but drained only slowly, or through the narrow straits of Denmark into the North Sea. The water that enters the Baltic stays there, on average, for 30 years. It accumulates. It remembers. What it has been accumulating for decades is nutrients. From the farmlands of Poland and Germany and the Baltic states, from the cities along its shore, from the atmospheric deposition of nitrogen from distant industrial sources, the Baltic has received more than it can process. The result is the largest anthropogenic dead zone on Earth. In the deep basins of the Baltic, the Gotland Deep, the Bornholm Basin, the Landsort Deep, the oxygen has been gone in places for decades, not seasonally, not temporarily, permanently. These are waters where the bottom has been anoxic for so long that the sediment beneath them has become layered with the chemical signatures of oxygen starvation, dark bands of sulfur, laminated like the pages of a slow history. The cod of the Baltic, once the basis of one of Europe's great fisheries, have suffered enormously. Cod eggs need well-oxygenated deep water to develop. In the Baltic's dead zones, the eggs die, and the species has been struggling for decades, caught between overfishing and a habitat that is no longer hospitable to its earliest, most vulnerable stage of life. And yet the Baltic is also a story of cautious hope. Since the collapse of the Soviet Union in the early 1990s, agricultural output in the eastern Baltic states fell sharply. Fertilizer use declined. Rivers ran cleaner. Scientists measured for the first time in decades a slight reduction in nutrient loading in parts of the sea. The recovery has been slow and uneven. The deep basins remain anoxic, but in some shallower areas, oxygen levels have stabilized. The lesson is not that the problem is solved, but that it responds, that the sea, given a chance, begins to breathe again. Further east, into ancient water. The Black Sea is one of the most isolated bodies of water on Earth. Connected to the Mediterranean only by the narrow Bosphorus Strait, it receives fresh water from some of Europe's great rivers, the Danube, the Dnieper, the Don, but exchanges saltwater with the outside world only in thin, slow trickles. This isolation has a consequence. The Black Sea is stratified not seasonally, but permanently. At around 150 to 200 meters of depth, there is a boundary, a halocline, a transition between fresh water above and dense, salty Mediterranean water below. Below this boundary, there's been no oxygen for thousands of years, not because of agriculture, not because of industry, but because of the sea's own ancient chemistry. This makes the Black Sea unique. Its deep waters are naturally anoxic, the world's largest natural dead zone. Below the oxic surface layer lies a vast, dark, hydrogen sulfide-saturated abyss that stretches to depths of over 2,000 meters. But in recent decades, human activity has pushed the boundary upward. A nutrient loading from the Danube and other rivers has intensified eutrophication in the surface layer. In summer, blooms form and die, consuming oxygen in the zone just below the surface, compressing the habitable layer between the eutrophic shallows and the anoxic deep. The northwestern shelf of the Black Sea, once a rich fishing ground, experienced severe oxygen depletion from the 1970s through the 1990s, driven by fertilizer use across Romania, Bulgaria, Ukraine, and Moldova. Catches of anchovy and sprat declined sharply, so jellyfish, which tolerate low oxygen better than fish, bloomed in extraordinary numbers, filling the surface waters in vast, pulsing mats. Then, again, collapse, this time of a different kind. The Soviet agricultural system fractured. Fertilizer use declined. And the northwestern shelf slowly began to recover. By the early 2000s, oxygen levels had improved. Fish returned. The jellyfish blooms faded. The Black Sea teaches the same lesson as the Baltic, written in older water. The system is dynamic. It responds. Here, what humans do on land changes what the sea becomes. Back to the Americas, to an estuary. The Chesapeake Bay is the largest estuary in the United States, stretching nearly 300 kilometers from the mouth of the Susquehanna River in the north to the Atlantic Ocean in the south. It is a place of extraordinary ecological richness. Or it was before the modern age rewrote its chemistry. In summer, the Chesapeake experiences hypoxia in its deep channel. Warm surface water sits over cool, dense, salty water rising from the Atlantic below. The two layers cannot mix. Nutrients from agricultural land across the watershed, Pennsylvania, Virginia, Maryland, New York, West Virginia, pour in through rivers and streams. The blooms that form are sometimes visible from space, and when they die, the decomposition is rapid and intense. The deep channel, sometimes only 20 to 30 meters below the surface, runs out of oxygen for weeks or months. Blue crabs, the Chesapeake's most iconic species, feel this keenly. They can swim away from hypoxic water, but the effort costs them energy and exposes them to new predators. Oysters, which filter the bay's water and were once abundant enough to clear the entire volume of the Chesapeake in less than a week, have been reduced to a fraction of their historical numbers. Their absence removes a natural filter that once tempered the bloom cycle. The Chesapeake has been the subject of one of the most sustained and politically complex restoration efforts in American history. Nutrient limits on farms, improved sewage treatment, wetland restoration. The results are mixed. Hypoxia persists, but in some years the dead zone is smaller than it was at its worst. And the bay improves in wet years when river flow dilutes the nutrients. It worsens in hot, dry years when stratification intensifies. Recovery, here, is measured in increments of millimeters per liter, in the slow return of submerged grasses, in the gradual expansion of oyster reefs. It is patient work. There are dead zones that do not come from agricultural runoff, that form not because of what humans have added to the water, but because of the ancient, powerful physics of wind and ocean current. Just in the Arabian Sea, the northwestern arm of the Indian Ocean, one of the world's most intense natural oxygen minimum zones has existed for millions of years. The monsoon drives this system. Every summer, the southwest monsoon pushes surface water away from the coast of Oman and Somalia. Deeper water rises to replace it, upwelling, cold, and nutrient-rich, fueling immense blooms of phytoplankton. These blooms are the foundation of one of the most productive fisheries on Earth. The sardines of the Arabian Sea, the mackerel, and the tuna that thread through its upper waters. All of them depend on this upwelling cycle, but below the productive surface, between 200 and 1,000 meters of depth, lies the Arabian Sea's oxygen minimum zone. A vast, persistent layer of near-anoxic water, maintained by the decomposition of organic material sinking from above, and the sluggish circulation that prevents oxygen from entering below. Creatures have evolved specifically to exploit this zone. Mesopelagic fish, lanternfish, bristlemouths, hatchetfish spend their days in the oxygen minimum, hiding from predators in the dim oxygen-poor water, rising to the surface only at night to feed. In recent decades, scientists have documented a troubling expansion. The Arabian Sea's oxygen minimum zone appears to be shoaling, rising toward the surface, and expanding in volume. Warmer surface waters hold less oxygen. Stronger stratification prevents replenishment. The breathless layer is growing. This is a natural zone being amplified by climate change, and its expansion compresses the habitat available to fish into an ever thinner surface layer, a squeeze felt most acutely by the creatures that cannot simply leave. On the other side of the world, in the Pacific Ocean, there are dead zones so large they shape entire ecosystems. The eastern tropical Pacific, the waters off the coasts of Peru, Ecuador, Colombia, and Central America, contains one of the most expansive oxygen minimum zones on the planet. It covers millions of square kilometers and extends from just beneath the surface to depths of nearly 1,000 meters along some stretches of coast. Here, too, upwelling drives the system. The cold Humboldt Current carries nutrient-rich water up from the deep along the South American coast. Phytoplankton blooms. Fish, anchovetas, ice in numbers almost beyond imagination, thrive in the sunlit surface layer. And below them, the oxygen minimum zone persists, ancient and patient. The anchoveta fishery of Peru is, in good years, one of the largest single-species fisheries in the world by weight. The fish are mostly ground into fish meal, protein for the chicken and pig farms of Europe and Asia. The economics of this system are vast and strange. The oxygen minimum zone of the Pacific is indirectly connected to the livestock markets of China. But the system is volatile. El Niño, the periodic warming of Pacific surface waters, periodically collapses the upwelling. The cold, nutrient-rich water stays deep. The surface warms. The anchoveta disappear. The coast of Peru during an El Niño event is a portrait of ecological stress. Dead sea lions on beaches, seabirds abandoning nesting sites, the smell of hydrogen sulfide rising from shallow bays where anoxic water has reached the surface. And then, La Niña returns. The cold water wells up. The fish come back. And the cycle continues for now. Let us drift now to the coasts of Asia, to waters fed by the largest rivers in the world, draining the most densely populated land on Earth. Every year, the Yangtze River, the longest river in Asia, carries the accumulated runoff of China's most intensively farmed provinces into the East China Sea. Hundreds of thousands of tons of nitrogen and phosphorus pour into the sea each year, feeding blooms that can cover thousands of square kilometers. The dead zone that forms at the mouth of the Yangtze is one of the largest in the world and has grown dramatically since the 1990s, tracking the expansion of Chinese agriculture and the increase in synthetic fertilizer use. In summer, hypoxic water covers much of the shallow continental shelf. Bottom-dwelling communities, sea cucumbers, clams, shrimp, are depleted across large areas. Yellow croaker, once abundant in these waters, have declined severely, overfishing compounding the stress of oxygen loss. To the north, the Yellow Sea and Bohai Bay receive runoff from China's northeastern provinces, grain-producing land of enormous scale. Bohai Bay is nearly enclosed, with limited water exchange, and its shallow, warm, nutrient-rich waters are prone to intense seasonal hypoxia. Fisheries in Bohai Bay have collapsed to a fraction of their historical levels, the result of overfishing, pollution, habitat loss, and oxygen depletion acting together in ways that are difficult to separate. The bay was once rich with prawns, crabs, and flatfish. Today, its catch is a shadow of what it was 50 years ago. The Bay of Bengal, bordered by India, Bangladesh, Myanmar, Thailand, and Sri Lanka, receives massive freshwater input from the rivers of the Indian subcontinent, including the Ganges and the Brahmaputra. This freshwater creates a strong surface layer that resists mixing, establishing conditions prone to seasonal hypoxia along the coast. The nutrient load entering the bay has increased significantly with the intensification of agriculture across the Ganges Plain, one of the most densely populated and intensively farmed regions on Earth. Seasonal dead zones form along the coast of Bangladesh and the Indian state of Orissa, affecting coastal fisheries on which tens of millions of people depend. On the Atlantic coast of Africa, between the equator and the southern tip of the continent, there's a system of coastal upwelling driven by the same trade winds that carry moisture across the Atlantic to the Amazon. The Benguela Current runs northward along the coast of Namibia and South Africa, one of the most productive upwelling systems on Earth. Cold, deep water rises to the surface, bringing nutrients that fuel blooms on a scale that is almost incomprehensible. But there is a dark side to this productivity. When blooms die and sink in the relatively shallow waters of the Namibian shelf, they create conditions for intense hypoxia. In some areas, the seafloor receives so much organic material that decomposition is near continuous. Hydrogen sulfide erupts from the sediment in events called sulfur eruptions, visible from satellites as iridescent green and turquoise plumes spreading across the ocean surface. During these events, fish die in enormous numbers, and the sea surface turns milky white with sulfur. The smell of rotten eggs reaches the shore. Fishers avoid entire stretches of coast. These are natural events driven by the extraordinary productivity of the Benguela, but they appear to have intensified in recent decades, possibly as warming waters and altered currents change the dynamics of decomposition and oxygen replenishment. Dead zones are not only a marine phenomenon. They form in freshwater too, in lakes, in reservoirs, in the slow, deep water bodies that dot the land. Lake Erie, at the shallowest and warmest of the Great Lakes, experiences severe summer hypoxia in its central basin every year. The basin is too deep to mix easily in summer and too shallow for cold, oxygen-rich water to persist. Nutrients from agricultural land across Ohio, Indiana, Michigan, and Ontario pour in through the Maumee and other rivers. In 2011, Lake Erie experienced its worst algal bloom in recorded history, a mass of cyanobacteria that stretched across the western basin for weeks, producing toxins that contaminated drinking water for 500,000 people in Toledo, Ohio. In 2014, the city had to shut off its water supply entirely. Africa's largest lake, Lake Victoria, has experienced severe eutrophication since the 1960s, driven by population growth around its shores, increased agriculture, and the introduction of the Nile perch, a large predator that dramatically altered the lake's ecology. Deep water hypoxia has expanded in Lake Victoria, reducing the habitat available to the native cichlid fish that once made this lake one of the most biodiverse freshwater bodies on Earth. More than 200 species of cichlid are believed to have gone extinct, a loss of evolutionary diversity with no parallel in freshwater biology. We have spent time with the losses. Let us spend some time with the survivors, because not everything dies in a dead zone. Life, in its ancient and stubborn way, finds the edges and the exceptions. Jellyfish, gelatinous, ancient, metabolically lean, are perhaps the greatest winners in a world of expanding dead zones. They can tolerate oxygen levels that would kill fish. They can feed on the phytoplankton that blooms in eutrophic water. They have no bones, no scales, no tissues that require steady, reliable oxygen supplies. In the Chesapeake Bay, in the Baltic Sea, in the Black Sea, jellyfish populations have expanded dramatically in the same decades that fish populations declined. And some marine biologists speak of a gelatinous sea, a world where the trophic pyramid has been inverted, where jellyfish occupy the upper layers that fish once commanded, recycling nutrients in inefficient loops rather than passing them up to tuna and dolphins and seabirds. This is not science fiction. In parts of the Baltic and the Black Sea, it has already happened. But jellyfish are not the only survivors. Polychaete worms, segmented, primitive, ecologically resilient, persist in low-oxygen sediments long after most other bottom dwellers have fled or died. And they burrow deeply, they slow their metabolism, and they wait. Some species have evolved the ability to store small amounts of oxygen in their blood, extending their survival into conditions that would be lethal for their relatives. Certain bacteria are the true masters of dead zones. Sulfur-cycling bacteria, Veggiatoa, and its relatives form white mats on anoxic seafloors, processing hydrogen sulfide in a chemistry that is as alien to us as anything on Earth. These mats can be meters thick in severely anoxic basins. They are, in their own way, kind of ecosystem. A simplified, ancient, chemically driven world that predates the oxygen-breathing life forms that came to dominate the planet. And at the very edges of dead zones, in the gradient where oxygenated water meets hypoxic water, where the boundary shifts with the season, extraordinary concentrations of life sometimes accumulate. Fish hover at the edge, feeding on the creatures below who are slowed and confused by low oxygen. Predators crowd the margins. There's a dark irony here. The dead zone, in its very edge, can create a feast. Everything we have described so far is, in some sense, a story of the past. But we must speak now of what is coming. Warming waters hold less oxygen. This is basic physics. Warm water is less able to dissolve gases than cold water. As the ocean warms, its capacity to carry oxygen declines, even before any change in nutrient loading. The oxygen minimum zones of the open ocean have been expanding for decades, not primarily because of agriculture, but because of temperature. A warmer ocean also stratifies more easily. The temperature difference between warm surface water and cool deep water grows, making mixing less frequent and less effective. The oxygen that phytoplankton and wave action produce at the surface has a harder time reaching the depths. Dead zones that currently form seasonally may begin to persist year-round. And zones that currently extend to 200 meters may begin shoaling to 100 to 50, pressing against the surface where the fish are, where the commercial fisheries are, where the food webs that feed billions of people are structured. These two forces, warming and eutrophication, do not simply add together. They amplify each other. A warmer ocean stratifies more, so the same amount of nutrients produces a larger, more persistent dead zone. A more eutrophied coast absorbs more heat at its surface, intensifying stratification further. But the system has feedbacks that our models are still learning to capture. This is not a reason for despair. It is a reason for clarity. The Gulf of Mexico dead zone exists because of decisions made by farmers in Iowa and Illinois. Change those decisions, reduce fertilizer application, plant cover crops, restore wetlands that filter runoff before it reaches rivers, and the Gulf dead zone shrinks. This has been demonstrated in years of low river flow, in years of reduced nutrient loading. The connection is real. Heat of the Baltic Sea has shown that political and economic change can reduce nutrient loading, even if the deep basins take decades to recover. The Black Sea's northwestern shelf has shown that recovery can happen faster than expected when the source of nutrients is reduced sharply and quickly. There are also biological solutions being explored. Oyster reef restoration in the Chesapeake Bay, mussel farming in the Baltic, where the mussels filter nutrients from the water and can then be harvested for fertilizer on land, a literal extraction of excess nutrients from the sea. She constructed wetlands at the mouths of rivers, mimicking the natural filtration that was destroyed when wetlands were drained for agriculture. In the open ocean, where warming is driving expansion of oxygen minimum zones, the solutions are necessarily different. Reducing greenhouse gas emissions is the only lever that changes the trajectory of ocean warming. There is no targeted intervention that can re-oxygenate the deep tropical ocean. The solution is the same solution required for every dimension of climate change: decarbonization, undertaken at a scale and speed that the world has not yet demonstrated. But in coastal and freshwater systems, where the primary driver is nutrient loading rather than temperature, there is genuine agency. The chemistry of the sea responds to what the land does. And what the land does is a matter of policy, of economics, of the choices that societies make about how to farm, how to treat wastewater, how to value the clean water that lies downstream of every decision. One of the quiet revolutions in our understanding of dead zones has been the development of monitoring technology. So that for much of the 20th century, scientists measured dissolved oxygen by collecting water samples from research vessels. Expensive, time-consuming, limited in coverage. A dead zone could change dramatically between one scientific cruise and the next, and its extent and dynamics remained poorly known. Today, autonomous underwater vehicles, Argo floats, gliders, profiling systems drift through the ocean continuously, measuring oxygen, temperature, salinity, and other parameters at regular intervals. Satellites track surface chlorophyll, inferring bloom dynamics from space. Sensors mounted on moorings on the seafloor transmit real-time data to shore. The ocean is becoming instrumented in ways that were inconceivable a generation ago. This matters because the ocean cannot speak for itself. It cannot send a distress signal when its oxygen drops. It cannot hold a press conference to announce that the bottom of the Gulf of Mexico has become, once again, uninhabitable. The instruments are our ears in a world we cannot directly perceive. Some of the most important recent discoveries have come from this expanded monitoring. The shoaling of the Arabian Sea oxygen minimum zone, detected only because of sustained, long-term observing systems in that basin. The expansion of oxygen minimum zones in the subtropical gyres of the Atlantic and Pacific, identified by comparing historical data from research vessels in the 1970s and 80s with modern autonomous float measurements. We are learning to listen to an ocean that has been changing faster than we knew. We have spoken of the giants, but dead zones exist at every scale. In the fjords of Scandinavia, the deep, by narrow inlets carved by glaciers, seasonal stratification creates hypoxic bottom water that traps and kills the salmon in aquaculture cages when the fjord's circulation temporarily stalls. Fish farmers in Norway watch oxygen meters with the same anxiety that a vintner watches a weather forecast. In the reservoirs of the American West, Lake Mead, Lake Powell, Shasta, stratification in summer creates anoxic bottom water that produces hydrogen sulfide and manganese, affecting the taste and safety of drinking water drawn from deep intakes. The dead zone here is not in the ocean. It is in the water supply. In the rice paddies of Southeast Asia, flooded, warm, rich, and decomposing organic matter, the shallow water above the soil becomes hypoxic in calm, odd-still air. The fish that once inhabited these paddies, scavenging insects and algae between the rice plants, have been largely eliminated by the combination of low oxygen and pesticides. In urban harbors, Boston, Sydney, Hamburg, Singapore, decades of sewage discharge created localized dead zones that suffocated the bottom life of the harbor floor. Many of these have improved substantially since the introduction of secondary and tertiary sewage treatment. The recovery of Boston Harbor, once described as the dirtiest harbor in America, is one of the quiet or environmental successes of the late 20th century. Dead zones, at every scale, respond to human attention, to investment, to the decision that the water matters. Long after the water above has recovered, the sediment below retains a record. Marine sediment accumulates in layers year by year, century by century. In anoxic bottom water, where there are no burrowing organisms to disturb the layers, these laminations are preserved with extraordinary precision. Each year's bloom, each year's die-off, each year's episode of hypoxia is recorded in the chemistry of a thin band of sediment. Paleoceanographers, scientists who study past oceans, drill cores from these sediments and read them like a book. The ratio of isotopes in the shells of tiny foraminifera tells them about past oxygen levels. The abundance of certain organic molecules tells them about past temperature. The presence of particular minerals tells them about past redox chemistry. From these cores, we know that dead zones are not a new phenomenon. Natural hypoxia has occurred in the geological past, in the warm, in sluggish oceans of the Cretaceous, when sea levels were high and continental shelves were vast and shallow and ocean circulation was weak. In the early Jurassic, ocean anoxic events left black shales across vast areas of the ocean floor, the preserved remains of a world where oxygen had retreated even from the open sea. These events are not directly comparable to modern dead zones, which are coastal and relatively shallow. But they remind us that ocean anoxia is within the system's range of behavior. The ocean has gone anoxic before. It recovered over millions of years. The life that exists today evolved in the aftermath of these events. We are not heading for a global anoxic event. The science does not support that conclusion. But we are heading for an ocean where oxygen is less abundant, where dead zones are larger and more persistent, where the breathable space for marine life is compressed in ways that will reshape fisheries and food webs and coastal economies. The sediment will remember this. Future paleoceanographers, drilling cores from the beds of estuaries and shelves, will read a signal in the chemistry of late 20th and early 21st century sediment, a signal of eutrophication, of a warming, of human activity written in the molecular language of the deep. We have traveled far tonight, from the warm green shallows of the Gulf of Mexico to the ancient anoxic depths of the Black Sea, from the shrinking oxygen layers of the Arabian Sea to the recovering waters of the Baltic coast. from the freshwater basins of Africa to the sediment archives of the deep ocean floor. What we have found in every place is a system that breathes, that requires oxygen to function, to sustain the extraordinary web of life that the ocean contains. A system that is in many places struggling to breathe. But what we have also found in every place is response. The system responds to what we do. The Baltic improved when fertilizer use declined. The Black Sea shelf recovered when agricultural inputs fell. Boston Harbor grew cleaner when sewage treatment improved. The Chesapeake Bay grasses crept back when nutrient loads were reduced, however partially, however slowly. The dead zones of Earth are not permanent features. They are not geological formations. They are dynamic, human-influenced, and in many cases reversible given time and given the decisions that enable recovery. This is the truth that the ocean offers us, if we are willing to listen to it. Not that the situation is simple, or that the solutions are easy, or that the recovery will be swift, but that the water responds, that the biology responds, that life, given the conditions it needs, will return. The shrimp will come back to the shelf. The cod will find their oxygenated spawning grounds. The grasses will creep across the seafloor once more, their blades swaying in currents that carry oxygen from the surface. And the dead zones, these places of absence, of stillness, of the breath held too long, may one day breathe again. Let that thought settle as the night deepens around you. The water is vast, the problems are real, and so is the possibility of a different outcome. The ocean is breathing, slowly, unevenly, but still breathing, and somewhere beneath its surface, even now, a polycate worm turns in the sediment, patient as the sea itself, waiting for the oxygen to return.